Hi there. I've been looking at infrared receivers and wondering how to control them. One way to do it would be to use a thing called the 555 timer. That's what this circuit is basically about. What I've got in the centre then is the 555 timer drawing. This is the pin out of it. It's got pin 1, 2, 3, 4, 5, 6, 7 and 8 because that's what the 555 timer has. It's a very old chip, been around an awful long time, but what I want to do is to be able to see if I can send a signal which will be detected by this infrared detector here. It's actually marked 9544.5 I think it is, but I think it's actually the same as an IRM 56384, the 38 corresponding to a frequency of 38 kilohertz, which is what some of these detectors work on. I've wired it up then as pin 1 to 0 volts, pin 2 to pin 6, pin 3 then is the output with the infrared transmitter on it, and that has a protection resistor in this case of 470 ohms. The pin 4 is used to stop it, so when that is switched on it will be stopped, and when it's open it will run. Across here pin 5 I haven't used. Pin 6 then, which was connected to pin 2, also connects to a 1 nanofarad capacitor and through a 10k resistor to pin 7. In fact, I've changed that, and the pin 7 I've used different values. Seem to work alright with 1010 and a 1 nanofarad, but I think the frequency was a long way from what I wanted, and therefore I don't think we got the distance. I won't be able to use it from the distance that I wanted to. I put a 680 microfarad capacitor across the power supply lines, but I think I got that wrong, because what I had to do here, if this is my detector, then I used 100 ohms up to the positive, 0 volts, the middle leg down to 0 volts, and the output pin through a 22k resistor to positive. But what I didn't put on there was a capacitor from 0 volts to positive to get rid of any spurious signals. So that's my 555 circuit, which hopefully will produce a waveform close enough to drive this detector. 555 is a wonderful thing. Spent a lot of time developing boards for it, so I thought I'd try a couple of those to see where I could get with it. So this is a board designed for prototyping. It has a 555 for use as an astable, as a monostable or a bistable, so it should be pretty easy to set up circuits using 2 or 3 555s. To see, on this one I've just used it for the one circuit. I've used the 10 and 10 on this particular circuit, and it did work. I also tried with this board over here, which is one that I built as an individual board, supposed to be multi-purpose, so that it could be used for anything that a 555 could do. So it could be used as a monostable, astable or bistable. And then, having done those, thought I'd move on and try to use, oops, if I don't throw it on the floor, this particular one. This is a very old circuit. It was actually, well, an old circuit board. It looks like it was made by somebody called CKW and may actually be nearly 50 years old. This was the way I used to do it back in those days, when we'd have a pen, an H-resistant pen, just draw onto the copper, dunk it in ferric chloride, and then we got our board. I've heavily modified this from what it was, so that I've got a massive capacity. Well, it's not that massive, it's only 220 microfarads, quite massive for today, quite common in those days. I've got a power in, I've got a diode so that the power, can't put the power the wrong way around. Might be better that way around with the positive on the top, I do like that. And then we've got the 555 over here. Here we've got a 1k resistor and then a 22k resistor. Come on baby, there we are. And then we have our capacitor down at the bottom. Those are the three timing components for the 555. I've just put sockets, round pin sockets on so that I can plug the outputs in and the power, well, anything from the power there. So that was one that I modified. It seemed to work okay. Once again, it's got the capacitor on it. But then I got back to looking at the 555, remembering what a wonderful chip it was, and remembered going to a meeting many years ago about the microelectronics in education. And this guy came along and said, oh, what we ought to be doing is analysing the 555, looking what's inside it, and that'd be great for teaching about electronics. Unfortunately, the chairman poo-pooed the idea, but afterwards I went away and yes, he had a good idea for teaching about the 555 because it contains lots of individual types of circuits that we can build it up from and understand what's happening. So we had comparators, we had NOT gates, we had AND gates, we had NAND gates, not an AND gate, wired together to make a latch so that when it's on it stays on and when off stays off, and then transistor to act as a discharge, and also an amplifier, which is the reason it can drive the LED without too much trouble. The way the thing works, it's quite nice because what it has actually is three resistors which are arranged in series and therefore act as a potential divider. So as they're the same size, some people say they're 5k and hence the reason it got its name 555, but according to the people that first produced it, that wasn't true at all. It just happened to be the number that came out. I've picked this up off a revision site, modified it a bit to show what I've done, and on mine I've put 1000 ohm resistor going on to pin 7, the discharge, which is through the capacitor, and 18,000 kilo ohm, an 18,000 ohm resistor, which is 18 kilo ohms, between pin 7 and pin 6, and then down at the bottom I put in a 1 nanofarad capacitor. The way this thing works from this website here is it charges up from 1/3 of the voltage, which is what we will get here because it's 1/3 and 2/3, and it will charge up until it gets to 2/3 of the voltage, when this will trigger and it will trigger this transistor on. It will then start to discharge through that transistor, so it charges up from 1/3 to 2/3 and then discharges again from 2/3 down to 1/3, repeating itself all the time. And while it's doing that, the output then is, while it's charging, the output's high, and then when it discharges, the output goes low. Fascinating thing, this website at Circuit Digest also has a calculator, so we can work out frequencies based on the components we've got. So if we have a 1 nanofarad capacitor, a 1 kilo ohm resistor as R1, which is the one here up at the top between pin 7 and pin 7 and positive, and if we had an 18 kilo ohm resistor between pins 7 and 6, then we would get a output frequency of 39 kilo ohms. kilohertz, sorry, frequency is measured in hertz. And the period, that's the time of length of the waveform, that's from this point here to this point here, would work out at something like 25.641 microseconds. This of course is absolute rubbish because this is electronics and we can't work to that sort of accuracy with electronics, because the components we use are probably a capacitor 20% error and 5% probably on our resistors. So this is very nice in theory, but in practice miles off. The fact that it's 39 kilohertz doesn't really matter, because if we look at the data sheet for these sort of things, we find that we get this Gaussian, is it, curve that we say. So at the 38 megahertz we would have a peak, and that's the maximum output we could get from it. But even if we went down to 32 kilohertz or up to 44 kilohertz, we could still get an output. The distance of course will be reduced significantly, but it should work, and in fact it does. So when I've been doing it, I've been looking at different values of resistors to put in, and what I found is essentially a 1K and an 18K would give me a period of about 24 microseconds, which would give me a frequency of about 41.66 kilohertz, whereas a 15K resistor would give me a frequency of about 47 kilohertz, and a 22K resistor should give me a 35 kilohertz signal. However, in the end I actually went for a 1K2 resistor and a 22 variable, and that's what I put onto this little board here. So I built this. I'd actually built this before, but I got all the wrong values on it. Nothing seemed to work, so that's what I've done there. A bit of Veriboard. Took most of the things off and replaced them. The idea being that when the button is pressed, if we switch the power on, then when the button's pressed it switches the thing on and goes off when it's off. So that is basically the way it works. My detector then, turn that power off. Now the detector's over here on this board here, which is going to my oscilloscope. Well, in fact it goes to a USB oscilloscope and my trusty cathode ray oscilloscope, which I think is, well, I don't know, I seem to prefer it. Maybe I'd be better learning about the USB scope, but what the heck. So what I have here then is the detector. That's wired onto this board, which isn't very easy to see. It's just a little breadboard type thing I built to go onto the USB scope so I can see what's happening. So yeah, that's as far as I've got with it. So let's have a look at the signals. If we move across then carefully, have a look at the scope. Can we get across there? If we look at the scope, what we got here is we've got our two tracers on the scope. Can I get it reasonable? Is that reasonable? So I've got the two channels set up. What I've got is the top channel is the infrared receiver, but on that time base is not good. But if I use a normal handheld television type remote, it gives me the signals, so I can see the signals are being received on the receiver. If I put my scope back to 5 microseconds, sorry, a signal, and then I transmit, everything disappears. Help. Oh, I have to switch it on, of course. And there, hopefully we can see at the bottom I've got my, if I can keep it on, keep the button pressed, I've got my signal across the bottom. If I turn it there higher, that's a different scale, that's the 20 microsecond scale, and that's the 5. And if I look at the 5, then I've got 5, 10, 15, 20, 25 and a little bit at this end, so it should be about my 26 millisecond. We notice that when I press it, what happens is the output goes low but then quickly goes back high again. And this is one of the things about these detectors. They don't stay constantly low. This one goes low. When I switch the device on, it goes low, and then when I let go, try again. When I switch on, it takes the output low, the receiver goes low, and then stays low for a fraction of a second and then goes high again. I did have a look at the time that this is low on my other scope, on my USB scope, and what I found there was that I got this nice trace that comes along and then goes back up again, and that's on 50 milliseconds per division, so it's low for about 1, 2, 3, 4, 5 divisions, so that would be about 250 milliseconds. So each time this receives a pulse, the maximum it can go low for is 250 milliseconds. So we can't use this as a burglar alarm or anything like that. We've got to keep pulsing it. So I could pulse it using a microcontroller, but that's something for another day. Quite enjoyed this. It's been a real trip back in nostalgia, looking back at the 555. Still seems an important chip, but of course it's given way to the microcontrollers, which I suppose are more interesting to most people. However, really interesting going back, having a look, but it's bye now. Bye.